In this video, I want to take a look at some algorithms that we will use for integer operations. So what I want to look at first is an algorithm for base B expansions, and this is an integer operation, so I've sort of misled you, but I wanted to go through the process that we have already gone through for a base B expansion, which we did in our previous video. So we're going to use just a problem I'm making up as I go here. Let's say I have 101 base 10 and I'm trying to convert that to base 2. So just to kind of show you what that algorithm does or what the algorithm says. Remember up here at the top, the procedure, all of this stuff is just sort of explaining where we start. So where I start is I've got a procedure that I'm naming the base B expansion. And then all of the stuff in parentheses is going to be describing variables. I'm writing very small, I apologize. Just describing variables. And then this over here kind of gives me a starting point. So it's like, hey, here's all the information that you need before we get to the actual procedure, which starts here at while. So the procedure is called base B expansion. I know that n and b will be positive integers, and b is going to be greater than 1. And I also know that my starting point for q, and q is my quotient, is going to be n, and remember n is the value that I'm starting with. So in this case, n would be 101. And k, which is actually our exponent, is going to start at 0. And again, what that means is the first time that I perform this procedure, which we'll get to the procedure in a moment, but we already know it from our last video, where I would take 2 times some number, which in this case would be 50, plus a remainder. So this k equals 0 is essentially saying when you get to the end, this 1 is going to be multiplied by 2 to the 0. Okay, so that's what the k equals 0 means. So now let's take a look at the while. So this is a loop, and basically what it's saying is it's going to continue through this loop over and over and over and over and over until q does equal 0. So it's saying while q does not equal 0, continue through this loop. So obviously once q is 0 or the quotient is 0, then you're done. So what does our procedure or algorithm tell us to do? It says that a sub k is going to be q mod b. Remember, that's just the remainder, and we defined that previously. So a sub k equals q mod b gives me the remainder. Q is going to be q divided by b. That's the quotient. So what it's telling us is essentially that a sub k, whatever's being multiplied by, k to, or the, sorry, base b to the k, is going to be the remainder. And it also tells us that q is going to be whatever the quotient was once I divided it by b, which tells me, hey, now use 50. And then this k equals k plus 1 means that now my exponent is going to be moving 1 more. So k is k plus 1. And so that's all this is telling us to do. And then basically it's saying, hey, keep going, keep going, keep going, keep going until q equals 0. So let's go ahead and follow it. Again, this would be 50, and then 50 would be 2 times 25 plus 0, and again, that's the implied times 2 to the first. Then I would take the 25. 25 is 2 times 12, which is 24 plus 1. I'm taking the 12, which is 2 times 6 plus 0. I'm taking the 6, which is 2 times 3 plus 0. I'm taking the 3, which is 2 times 1 plus 1. And then I'm taking the 1, which is 2 times 0 plus 1. And since I got to this point where my quotient was now 0, that's when it tells me to stop. So then what it tells me to do, and that's the outcome, so this is the output, is the return. So what is it going to return? It's going to give me essentially all of those values. So again, we're going to start, and then let me go ahead and just kind of number these so we remember. 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth. So basically what it's saying is we're going to start at 2 to the sixth, which is here. So I'm going to say a to the k minus 1 is 1 times 2 to the sixth. And it's also going to give me 1 times 2 to the fifth. And it's going to give me 1 times 2 to the fourth, or sorry, 0 times 2 to the fourth, etc., etc., etc. And so basically that is going to be the outcome, which is the base B expansion. So hopefully we sort of understand the pseudocode for this algorithm. Now let's take a look at a new algorithm, and that algorithm is the addition algorithm, and we're just going to look at it for binary, but obviously it would be the same process for other bases. So essentially the algorithm tells us to add A and B, which are, basically two values that are in binary, so they have to be in the same base. We're first going to add their rightmost bits, and so that's telling us to take basically the rightmost bit of A and the rightmost bit of B, and that's going to give us, and again 2 because we're dealing with binary, so we're taking some value times 2 plus some value. And so over here I've written a little note to let you know that S sub 0 is going to give me the new rightmost bit, or the rightmost bit, of my solution. So this is the rightmost bit of the solution. And the C sub 0 is the carry. So obviously for binary, my carry is going to be 0 or 1, which means just like when I do normal addition, what am I carrying over? Then I'm going to take the next two, so not the ones to the far right, but the ones just to the left of that, and I'm going to do the same thing. Notice here I'm taking those 2 bits as well as the carry, which makes sense because if we carry, that means we're taking it to the next space over. And again, notice the format is going to look the same. I'm going to have a carry, I'm going to have my next rightmost bit of my solution, etc. And I'm going to continue and continue and continue until I get to my last bits, basically. And once I've added the last bits, I'm going to find my final solution. So I'm going to add A to the n minus 1 plus B to the n minus 1 and C to the n minus 2, which is that last carry, to obtain that final solution here, keeping in mind that if I do end up with a carry, that I need to then, of course, carry that over. Now this is all well and good, but it makes much more sense when we actually look at an example. So let's do that. So here's an example of that addition algorithm that we just talked about, and I've already sort of written it out for you, which I usually don't like to do, but I just wanted to make sure I didn't make an error and throw anybody off. And so here's what the algorithm tells us to do. It says we're going to take, for the first value, so notice here I've said S sub 0, is essentially saying take the first 2, that's the rightmost bits. And so notice I've underlined those with orange in my original question. I've got A is 1 and B is 0, so notice here I'm taking 1 plus 0. I'm adding those together, and of course that sum is 1. And so what I want to do is then write that in the correct format, which says how many 2's do I have, which in this case would be 0, and then what would be the remainder? And the remainder here would be 1. Now remember that 1 is going to be part of my solution. Then I do the same thing. I'm looking now, and I've underlined these in green, at 1 and 1, but I also have to take that carry from the original or from the step before. So here notice I've taken 1 plus 1 plus 0, which came from here. 1 plus 1 plus 0 is 2, and so again, as I'm writing this out, I'm saying how many 2's do I have? I have 1 2, so 1 times 2, and do I have anything left over? No, I don't. Again, that 0 is going to become part of my solution. Then I'm just essentially repeating that process over and over. So now I'm looking at the pink ones. I don't have a pink marker, so I guess we'll use red. And I'm saying, looking at, 0 for A and 1 for B, 0 and 1. And then I'm also taking the carry from the step before, which is 1. And that gives me 0 plus 1, which is 2. So again, I'm saying how many 2's do I have? I have 1 2, and then that does not leave me a remainder. So again, that gives me another value in my solution. And then I'm looking at the leftmost digits, so 1 plus 1. And then again, I'm taking the carry of 1, so 1 plus 1 plus 1 is 3, which means I have 1 2, but then I still have 1 left over. And then it's easy to just say, okay, we're all done here, but keep in mind, I still have a 1, which I need to make sure I'm not just getting rid of. And so on the next step, I'm then again using my 1, and that gives me my solution. So my solution again is sort of, I have to go bottom up just as I did before. So it's 1 1 1 1 0 0 1. Now this algorithm is great and all, but what I think, I mean, it's essentially the same thing, but if I were actually going to have to add these together, 1 0 1 1 plus 1 1 1 0, I would actually just add them old school, keeping in mind that this is base 2, so if I add two values together and I get a 2, then that means I have to use 1 0, which basically means I'm just carrying the carryover, just like I did in the algorithm. So let's take a look at this. I'm going to take 1 plus 0, and that gives me 1. So no carry on that one, I don't have to worry about it. Here I get 1 plus 1, which is 2, and 2, remember, is equal to 1 0 in binary, and so I'm going to put the 0 here and carry the 1. Then I'm going to take a look at 0 1, but also the 1 that I carried. And so I'm going to be looking at 1 plus 0 plus 1. 1 plus 0 plus 1 is 2, which again is 1 0. So here I'm going to put a 0. Here I'm going to put a 1. And then I'm going to look at 1 plus 1 plus 1, which is 3. And so I can think of 3 as 1 1, and that's where I would get the 1 1. So again, as a person, it makes more sense to me just to knock it out and do it this way. But remember that that's not a lot of times what algorithms are about. We are trying to create, a code or an algorithm for the computer, so specific steps for the computer to follow, and that's where that algorithm came from. So let's take a look at now the pseudocode for that algorithm. So again, the pseudocode is just a representation that we would give the computer of the exact same procedure we just talked about. So the procedure is adding. We know A and B are positive integers. And remember anything, and I'm sorry I should have written this in green, but this is just, hey, here's a note, and that's for people, not for computers. And then I'm basically saying, let's start with C equal to 0. And then I'm saying for J, and in this case we're using J instead of I sort of as our index, so that's our counting measure. So from the right side to n minus 1, which of course we would never go up to n because in say a base 2 we only go 0 to 1, we never go to 2, etc. And so essentially what it's saying is that the divisor is the two values plus the carryover. And so again, the initial carryover is 0 divided by 2. And this is the floor function, because obviously we're looking for that least value. And then if there's anything left over, that's going to be your remainder. And so the S sub j then, which means your solution or the value that you're going to use, which is essentially the remainder, remember, because that's what we were looking at, is just the remainders, is taking aj plus bj plus c minus 2d, so minus 2 times whatever that divisor was. So we have to take that away to see what's left over as a remainder, and then c is equal to the divisor, which basically means start the process all over again. And then Sn, so for each value that's equal to c, and the return is our solutions. I want to go through a multiplication algorithm example with you. I know I have not given you the algorithm yet, but the way the algorithm is written actually just overcomplicates everything. So before we actually look at the algorithm, let's just remember from way back in the day when we used to actually do multiplication like this. And when we did multiplication like this, we would take that rightmost digit of the bottom number and multiply it by every value above. So 0 times 1 is 0, 0 times 0 is 0, 0 times 1 is 0. Then what we would do is we would leave a 0 as a placeholder. And then we would take that next digit and repeat the process. So 1 times 1 is 1, 1 times 0 is 0, and 1 times 1 is 1. And then we would leave 2 placeholders, which is essentially shifting it over, and then 1 times 1 is 1, whoops, different color, let me try that again, 1 times 1 is 1, 1 times 0 is 0, 1 times 1 is 1, and then we would just do our addition, which thankfully we've already learned how to do, and that would give me 0 plus 0 plus 0, which is 0, 0 plus 1 plus 0, 0 plus 0 plus 1, 1 plus 0, and 1. So my solution is 1, 1, 1, 1, 0, base 2. Easy enough, right? Well, now let's take a look at the process we would go through using the algorithm, and you'll see that's incredibly similar to what we just did. So the algorithm says you're going to take A and you're going to multiply it by the rightmost value of B. And so just as we did before, A is 101 base 2, and I'm multiplying that by the rightmost value of B, which is 0. And then, of course, I am going to multiply that by the base, which in this case is 2, to the k, which is 0. And I'll go ahead and find those solutions in just a moment, but let's continue with the algorithm and the way that we would continue this. Then I would take A times B to the 1, or B sub 1, excuse me. So this is 101 base 2 times my next value is 1. And 2 to the first, because remember that's going to match the place value that we're using. And again, I'll come back to that solution in a moment. And then I'm going to take A times B sub 2, which is 101 base 2 times, it looks like we're looking at a 1 again, and this time it's 2 to the second. And again, I'm going to find all of those values. And so what I want you to see is going to happen is I'm going to end up with the same answers that I had right over here. But let's go ahead and take a look at that. So if I took 0 times 2 to the 0, that would be 0. So I'm going to take 0 times 1, which is 0, and 0 times 0, which is 0, and 0 times 1, which is 0. Then I'm going to, on the next one, take 1 times 2 to the first, which is 1. So I'm going to take, 1 times 2 to the first, which is 2. I'm going to take 2 times 1, and 2 times 1 is 2, but remember in base 2, 2 is equal to 1, 0. And so that's going to give me a 0 here with a carry of 1. And then I'm going to take 2 times 0, which is 0, and add that 1 that I carried. That gives me a 1. And then I'm going to take 2 times 1, which is 2, but remember 2 is written as 1, 0. And so far we can see that this gives me 0, 0. This gives me 1, 0, 1, 0. And then looking at the last one, I've got 1 times 2 squared, or 1 times 4, which is 4. So now I'm taking 4 times everything. 4 times 1 is 4. How do I write 4 using binary? Remember that would be 1, 4, and 0 2s and 0 1s. So essentially I'm going to write my 0 and I'm going to have to carry that 1, 0. Then I'm going to take 4 times 0, which is 0, and I'm going to add the 1, 0. And so that means I'm going to write the 0 and carry that 1 over. And then I'm going to take 4 times 1, which is 4, and I'm going to add the 1, which is 5. How do I write 5 in binary? It's a 4 and a 1, so 1, 0, 1. So what I want you to notice is not only am I getting the same solutions that I did when I did it the old school by hand way, but I'm also, basically what's happening here is it's shifting it over one place, shifting it over 2 places. So that's all that's happening. And then of course to find my solution, I'm just going to add, just like we did before. And so I'm going to add 0 plus 0 plus 0, which is 0, 0 plus 1 plus 0, 0 plus 0 plus 1, 1 plus 0, and 1. And notice I'm going to get the exact same solution, which is really the exact same process. It's just written in a different way, but we should be very familiar with the way it's written because we've done a lot of practice in this format. So looking at the pseudocode for the multiplication algorithm, again, it's saying exactly what we did on our last slide. It's saying, here's the procedure, which is to multiply. We've got a and b, which are positive integers. They're saying for, basically starting at the value furthest to the right through the rest of the values. If the b value that we're multiplying by is 1, then everything, our value, is going to be a shifted over j places. So cj being when we said equal to whatever, they're saying, okay, let's shift it over that many places. Otherwise, we get 0, and p is 0, p being the product of ab. And we're going to continue through the cycle over and over and over and over and over. And then essentially what we're saying is here, add up all of the p's from before, plus cj, which is, remember, all of these. So they're saying take all of these and add them together, and that is your return. Let's look at the pseudocode for computing the divisor and the mod, essentially, which is computing the remainder. So we're already very familiar with this. Again, we're calling this the division algorithm. We're not going to do an example of this one because we've already talked about the division algorithm, but essentially we're saying a is an integer, d is a positive integer, just as we had said before. Q is the quotient, it's going to start at 0. R is the remainder. It's going to start as the absolute value of A, which means we want to make it positive. And what we're saying is while R is greater than or equal to D, then the remainder is going to be R minus D, and the quotient is going to be Q plus 1. So this is basically saying if we're dealing with a positive value, or here if we're dealing with an A is less than 0, so we're dealing with that value that we're starting with being a negative, then things change a little bit. So remember when we actually did examples of these, you would have to go essentially one more than you might think and then add a remainder, and that is so that a remainder would be a positive value. Remember, we always want our remainder to be positive. So this is just sort of outlining the steps that we've already gone through, and of course our return of this is that we would get the quotient and the remainder. So let's take a look at the modular exponentiation algorithm, which is the last one we'll look at together. And this one is super important in cryptography, and so we definitely want to make sure we go through this. And again, what I'm looking for is essentially to take a value and to a power in whatever mod I want. And obviously for small values it's very easy to do, but we want to be able to do this for large values of b, n, and m. So let's sort of go through this process together as to how we arrived at our final algorithm, which is here, but let's look at where it came from. We know, because we've already been working on this, that I can take any number that I want and I can write it in an expanded form. So I can say, 2 times 3 squared plus 1 times 3 to the first plus 1 times 3 to the 0, etc. That's what we've been working on for a while. So that's just me writing that out again. Then we're going to use something probably from way back in Algebra 2 called exponentiation. And exponentiation is essentially taking the values that we have on each side of our equal sign and making them exponents of a certain base. So in this case, I'm taking a base of b on each side, and I've taken the expression of n on the left and making that an exponent, and I've taken the expression of all of this business and made that an exponent on the right side. But as we can see on the right side, I've got just this really, really, really long exponent that's not super helpful. So instead what I'm going to look at is being able to turn that into smaller, more manageable bits. And we know the same way that I could say 2 to the third is the same as 2 squared times 2 to the first, because we add those exponents. I know I can take, because these exponents are being added, I can kind of go in the opposite direction. So I'm going to call this b to the a k minus 1 times b to the k minus 1, and then I'm going to multiply it by the next value and the next value and the next value, etc., until I get to the end. So this is the actual algorithm that I'm going to use, and I want to show you what that's going to look like if I actually did this. Now I'm giving you a sort of a silly example, because in real life you would just grab your calculator and take 3 to the 11th. But here's how the algorithm works so that you understand the algorithm. The algorithm says take your exponent and turn it into a binary value. So I have the number 11, which currently is base 10, and I want to write that base 2. So we'll do it the same way that we've done before. We'll say how many 1s, how many 2s, how many 4s, how many 8s, etc. So if I were taking 11, that would be an 8, which would leave me with 3 left over, which means I don't need any 4s, but I still have 3 left over, which means I need 1, 2, which leaves me with 1 left over, which means I need 1, 1. So here's my value, my exponent, now written binary. And so what this algorithm tells us to do is to take, and again, I'm just going to reiterate that, remember, in binary, 2 to the 0 is 1, and 2 to the 1 is 2, and 2 to the second power is 4, and 2 to the third is 8. And so essentially what I'm going to do is I'm going to take 3 to the 8th. So 3 to the 11th equals 3 to the 8th, because there's one of those. There are no 4s, so I'm going to skip that one. There's 1, 2, so times 3 squared. And there's 1, 1, so times 3 to the 1st. And then I would find each of those products, which is 6561 times 81 times 9 times 3, and when I multiply all of that out, I get my solution. Now again, for 3 to the 11th, because I've asked you to find it mod 10, it would not make sense to do it this way. I could just put it in my calculator. But we're going to look at examples where you can't just put it in your calculator, or the base is not 10, etc., but you're still going to be looking at that exponent in binary. So finally, let's take a look at the pseudocode for modular exponentiation, and then of course an example as well. And so the procedure, again, modular exponentiation. B is an integer, n is essentially a binary string, so we've got all of our binary values there. M is positive integers. This tells us x starts at 1, and the power starts at b mod m. And then it says basically for all of the values, so for the index of 0 through the rest of them, if a is equal to 1, a sub I is equal to 1, so for that index, if the value is equal to 1, then x is going to be x times the power mod m, and the power is going to be the power times the power mod m. And you're going to, again, continue through this loop again and again and again and again until you've gone through all of the values. And our return will be x, which will be b to the n mod m. So let's take a look at an example where we want to find 3 to the 6th mod 5. Now before we actually do this using the algorithm, let's take a look at 3 to the 6th. 3 to the 6th is 729. If I wanted to know 729 mod 5, I would divide it by 5 and find the remainder, and of course that would be 4 mod 5. So I know that my answer should be 4 when I get to the end of this. But again, I want to make sure that my algorithm returns that value. So let's take a look at the step-by-step in case you're still struggling a little bit with the pseudocode. What this tells us here is that x starts at 1 and the power starts at b mod m. So notice here I've written that x begins at 1 and the power begins at 3, which was my base, mod 5. And 3 mod 5, obviously if I took 3 divided by 5, that would be 0 with a remainder of 3. So I've got x is 1 and the power is 3. Then I have to look at 6 as my exponent, and again I want to look at 6 as a binary. So 6 in binary, or base 2, means I have 1 4 and 1 2 and 0 1s. So it's 1 1 0 base 2. So those are the values that I'm using. So I'm beginning at my first value, which is 0, and since a sub 0, or a of 0 equals 0, nothing is done to x because it doesn't tell us anything to do to x over here. But for the power is going to change no matter what. So the power says power times power mod m. And so my power before was 3, so notice I'm taking 3 times 3, which is 9, mod 5, which is 4. So now I still have x is 1, that hasn't changed, and now my new power is 4. And then I'm just repeating that process. So now I look at the next one, and the next one says 1, so since a is 1, x does change, and x is the power that the x that I had before, multiplied by the power, which is 4, so 1 times 4, mod 5, which is 4. So my new x is 4. And then my new power is taking my power times my power, mod 5. So 4 times 4 is 16, mod 5, which is 1. So now I've got 4 and 1 for my x and for my power. And then I look at the next one, which is 1, and that says that x will now be 4 times 1. So again, 4 times 1 came from x times the power, so 4 times 1, mod 5, which of course is 4. And the power will be the power times the power, mod m, and my power before it was 1. So 1 times 1, that should be mod 5, I apologize. Mod 5 is 1. And so my return is going to be whatever that last x is, and so notice my return is 4, and that's exactly what I wanted it to be.